Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an interesting exponential, well, I should probably say exponential and trigonometric at the same time equation. We have e to the power iz equals cosine of z, and we're going to be solving for z. Okay, great. Let's see how many methods we can come up with, and I'm pretty sure you're gonna find out or discover something that I haven't thought of, because you guys are really good at this. Okay, great, good job. Now we have e to the iz equals cosine z. When you see something like this, you should almost immediately think about the polar form, the trigonometric form, and Euler's formula, right? Obviously, Euler is a great mathematician. He's done a great deal of things, which is probably very much unparalleled. Anyways, so we have this equation. How can we handle it? E to the iz equals cosine of z. There's a couple of ways to go about it. Let's go ahead and use the first method first. So the first method is going to look like this. We have an identity for cosine z. If you remember, we talked about this in lecture videos too. Go ahead and check them out if you haven't done so. But cosine z can be written as e to the iz plus e to the negative iz divided by 2. We're going to talk about the reasons later, because I just want to use this without giving away too much, and then later on when we do the other methods we're going to have a better idea. Okay, so let's just plug it in. I have this for the right hand side, and the left hand side is going to stay the same. E to the iz is equal to e to the iz plus e to the negative iz divided by 2. This is really nice because this kind of takes the trigonometric problem from trigonometry to another realm, right? Which is the exponential. Nice. Everything is of the same kind. We can go ahead and cross multiply here. 2e to the power iz equals e to the iz plus e to the negative iz. Awesome. What should we do next? Subtract like terms. Bring this over here. And that's going to give you e to the iz, 2 minus 1 is 1, equals e to the negative iz. Which is kind of like an interesting equation, right? If you think about it, how can something like e to the power something equals e to the power negative power something? Well, it can only happen if z is 0, right? But why? Let's find out. So one thing we can do is multiply both sides by e to the iz to get rid of the e to the negative iz on the right hand side. This is going to give me e to the 2iz, iz plus iz, equals e to the power 0, which is 1. Awesome. Because these are reciprocals, right? Again, we're going to talk about this in a little bit later. So we got the following equation. Let's rewrite it. E to the 2iz equals 1. So our equation, which is kind of interesting, right? We had e to the iz equals cosine z, and then it's as if we squared both sides, and from cosine squared we got 1. That's kind of interesting, because what happens is if you square both sides here, you get e to the 2iz equals cosine squared z, and we have e to the 2iz equals 1, which means cosine squared z is equal to 1. And then from there you can proceed as follows. So I didn't even plan this out, but this just came up. Now this gives us two solutions. Cosine z is 1 and cosine z is negative 1. Great. We kind of need to check these solutions, right? Because we squared both sides, and squaring sometimes changes things. Okay? We got to make sure this satisfies the original equation. Do you think it will? Well, we're going to find out. But let's go ahead and take a look at another alternative. This is still the first method, I believe, but we can kind of go a different route, right? After this, we got e to the 2iz equals 1. And the normal method, I mean, you can definitely, you're more than welcome to use it. And this is kind of nice because we're not using an identity, but we're using what's given in the problem, right? Makes sense? Cool. Now, e to the 2iz equals 1. And I want to write 1 as e to the power 2 pi n I, where n is an integer. Make sense? So this identity is true because 1 can be complexified. If you think about the Argand plane, 1 is going to appear here. This is imaginary, and this is real. So 1 is real, and it's 1 units away from 0. Makes sense? And it makes the 0 radians or 2 pi radians or any multiple of 2 pi radians. Makes sense? That's what 2 pi n represents. Multiple of 2 pi, an integer multiple. So now this kind of gives us something super nice because 2 cancels out, I cancels out, and z happens to be n pi, where n is an integer. So what is that supposed to mean? It just means that z can be 0, z can be pi, z can be 2 pi, 3 pi, so on and so forth. Obviously, it can also be negative pi or negative 2 pi, but it has infinitely many solutions. That's what happens most of the time with complex numbers, because complex numbers are just awesome. Make sense? Okay, cool. That's kind of like the first method. And again, you can go off of this, but here's the idea. I want to tell you something after finding this n pi. If z is a multiple of pi, its cosine, think about it. If it's 1 pi, its cosine is going to be negative 1. If it's 2 pi or 0, it's going to be positive 1. You see, it's going to oscillate. That's why this solution is also valid. Make sense? Okay, obviously from here you could find the same thing, but it would take longer because you would have to look at these two equations separately, or you could take this and use that with a double angle identity, such as cosine of 2z equals 2 cosine squared z minus 1. And from here, you can plug it in and find cosine, which is first power, by the way. No extraneous solutions are going to occur. Anyways, you get the idea, hopefully. Hopefully, I'm not confusing you by giving you too much information overload. Okay, so let's go ahead and take a look at an alternative method. We have e to the iz equals cosine of z. Again, as soon as you see e to the iz, you should think of the following. Cosine z plus I sine z. Why? Because Euler said so. You have to follow him, right? And that equals cosine of z because that's what's given in the problem. Again, this is not an identity, it's given. Now, take a look at this and take a good look. Take a good picture. Cosine z cancels out, and we end up with a 0. Beautiful. 0 is really good if you're solving an equation. You want to get 0. Now, I sine z is 0, and we know that I does not equal 0, so divide both sides by I. You get sine z equals 0. And this means the following. Think about the unit circle. Sine is 0 at 2 points, here and here, on the x-axis, right? Because that's where cosine is max and min. Make sense? In other words, z from here is just going to be n pi, where n is an integer. As before, of course, it's going to be the same solution. All right, great. I don't know if I did come up with a solution from Wolfram Alpha, but I believe I did. Here we go. The alternative form, we talked about this, did we? Yes. And the second one is going to be the solution. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.